Good afternoon, everyone. Welcome to today's ICorr Midlands branch technical webinar. My name is Ali Morshed, and it's my pleasure to host today's session on dry gas pipeline internal MIC, case studies, root causes, and remedies. Thank you all for joining us. We have participants from across the world and various disciplines, and we greatly appreciate your continued support for ICorr technical events. Before we start, there are a few points that I want to mention. Today's presentation will be recorded and uploaded to the ICorr Midlands YouTube channel. I encourage you to visit the channel and subscribe to access our other webinars. This session will run until approximately 4:35 p.m. UK time, followed by a Q&A session until 5 p.m. And please submit your questions at any time during the Q&A function so we can read it to the guest speaker and answer your question. We also encourage technical discussion and will endeavor to address as many questions as possible during this session, but this option is for you to reach out to ICorr Midlands or the guest speaker after the meeting. CPD credits are available on request through the ICorr Midlands branch via the email address provided in the webinar's announcement confirming the attendance. And lastly, our next webinar is scheduled for 23rd of July at 4 p.m. UK time and will cover the validation of current magnetometry inspection, CMI, for pipeline corrosion assessment, which will be delivered by Mark Glinka from AMPP. And we'll share further announcements soon through our social media channels and by email. So without further ado, we get to today's webinar, which is about microbiologically induced corrosion, which is a critical degradation mechanism in pipelines where microbial activity accelerates material loss and can lead to localized corrosion, pitting, and premature failure. So as you know, there are different microorganisms such as sulfate-reducing bacteria, which can generate corrosive metabolites, and they can cause leakage from the pipeline and can cause lots of risk and unplanned shutdown. The presentation today will explore the mechanism responsible for microbial activity in systems traditionally considered low risk. And with regards to the speakers today, it's now my pleasure to introduce our speaker, Dr. Ali Morshed, who is a highly respected corrosion specialist with more than 23 years of industry experience, having started his professional career in the oil and gas in 2002. Over the years, he developed extensive expertise across multiple industries and geographic regions. He is the developer of Morshed corrosion management model and the author of several internationally recognized corrosion management publications, including 5 books on corrosion management and a dedicated book on microbiologically influenced corrosion, published through AMPP. So, Ali, thank you very much for joining us today. The floor is yours for the presentation.
Ali John, or shall I say Dr. Morshed, thank you very much for your very kind introduction. It's a great pleasure to be here with you and our dear audience. I would like to thank everybody for joining us in a very busy time. I know most of us are very busy watching the World Cup. Anyway, if you can kindly confirm that you can see the screen, I will start my presentation.
Yes, the screen is visible. If you, please start.
Okay, yeah, thank you very much. So today I'm going to talk about several MIC failure cases associated with gas pipelines, and we were very surprised to see that in a system where we were not supposed to have any water, we were getting microbially induced corrosion inside the pipeline. So what I'm going to do, I'm going to briefly discuss MIC And here we have got a footage of a gas leak we had in a rural road. As you can see, the gas is gushing out. And unfortunately, we had quite a number of failures because of MIC. And it became a challenge for us to find out where the water was getting into the system and where the bacteria were going into the system. So what I will discuss, I will briefly mention a few basic facts about MIC. Then I will start the main body of my presentation discussing this gas distribution network where the MIC cases had created a few failures. And then I will go through the root causes and finally a couple of associated recommendations. There are a number of agents which promote internal pipeline corrosion, and they are carbon dioxide, hydrogen sulfide, elemental sulfur, oxygen, chlorides, organic acids, bacteria, and solid particles. And in case of solid particles, we all know that they can cause erosion, under deposit corrosion, or they can further promote microbial-induced corrosion. There are a number of pipeline standards published by various organizations which cover the topic of internal corrosion. As you can see from the table here, we have got a number of NACE or AMP standards, a couple of ASME standards, one API, and two ISO standards. I'm not suggesting that these are the main standards covering the internal corrosion of the pipelines, but these are the standards which I've been using most of the time over the years. And what I would like to highlight here is this ASME B31.8S, the supplement which was published after the ASME B31.8 had been available for a number of years. It's called Managing System Integrity of Gas Pipelines. And what I would like to highlight about this particular standard is that it looks into corrosion and corrosion control from a brand new angle. For instance, in one of the sections, it discusses the significance of communication between different parties in order to have a better corrosion control system. And communication is a topic that unfortunately is not covered very much, neither in our university books nor in many of the standards which focus on the topic of corrosion control. So that brings me to the MIC section. These are just very few points I would like to mention. Corrosion, MIC could be defined as the corrosion initiated or promoted by the presence or activity of microorganisms or both. Bacteria are divided into two main classifications, planktonic and sessile. What we have to take into consideration here that when we deal with bacteria, there are different ways of classifying the bacteria. We can classify them based on their shape. We can classify them based on their metabolism. Here, I have classified them based on their mobility. Planktonic ones are the ones which are floating in the system. Sessile ones are the ones which are already stuck to the metal surface. It is the sessile bacteria that promote MIC at metallic surfaces. Killing planktonic bacteria is significantly faster, easier, and cheaper than killing sessile bacteria. Again, it's a very simple point. Most of us know this point, but what has been surprising me over the years is that many oil and gas operators which have to deal with MIC, unfortunately, still do not distinguish between sessile and planktonic. And in some of their companies, the policy designed to mitigate MIC only covers the planktonic bacteria, which is, as I said, faster and easier and cheaper to kill than sessile bacteria. And their protocols, their corrosion management protocols are all formulated based on planktonic bacteria. They do not take into account sessile bacteria. Presence of water is a prerequisite for bacterial survival and activity. Again, it's very important point. It's a very important point. No water, no MIC. Prevention is better than cure because microbial control, once lost, may take years to restore. This is something we have to remember when we commission a new asset. It's worth maintaining a corrosion control system in such a way that bacteria and MIC are not introduced, because once they enter the system, it will be extremely difficult, if at all, that we can get rid of them. MIC corrosion rates could exceed 5 millimeter per year. I have myself come across this rate, but I've heard that MIC corrosion rates could be as high as 8 millimeter per year. So for a new system with a 3 millimeter corrosion allowance, that means that the corrosion allowance, the whole thickness of corrosion allowance could be gone in less than 6 months. MIC is highly localized and often manifests itself at the 6 o'clock position of our system, or here we are talking about the pipeline. So if we get MIC, we expect to see them, or we expect to see the failures at the 6 o'clock position. So to recap, in order to have MIC in our systems, we have to have water, we have to have nutrition, and we have to have favorable conditions for the bacteria. And by favorable conditions, I mean the right temperature, stagnation, pH, and salt content, as not all the bacteria can function and stay active in unfavorable temperature, pH, or salt contents. And needless to say that stagnation is extremely important. This is the factor which helps the planktonic bacteria to become sessile bacteria. And here we have got a picture of a typical bacteria. You can see we have got a unicellular entity which is connected to a very long tail, and the tail helps the bacteria to move into areas where there is a higher concentration of nutrition, or it helps the bacteria to distance itself from the areas where we have got unfavorable conditions, like concentration of chloride or biocide in the system. And after that very brief introduction to MIC, I look into these gas distribution systems. Natural gas production and delivery encompasses a very large system. It starts from the wells, whether onshore or offshore wells, and goes all the way to the consumers, being both industry and household customers. And the area which I'm going to talk about covers bits of the transmission systems and bits of the distribution systems, and these comprise both piping and pipelines. Of course, here I'm more concerned about the pipeline section. So, dry gas pipelines at a glance. A gas company is usually located downstream of a gas refinery and delivers gas to household and industrial customers. Pipelines carry dry natural gas, and by dry, I mean any gas phase which has got less than 7 pounds of water in every 1 million standard cubic feet of gas, or less than 112 milligram of water in 1 million cubic meter of gas. So these are two definitions for a dry gas pipeline. And a typical downstream dry gas network consists of more than 10,000 kilometers of pipelines and piping. So it's a huge system. And this 10,000 kilometers is not even an average, is minimum. In some cases, the pipeline network and the piping network is much, much bigger. So the question we have had is that we were encountered with increasing number of MIC failures in our gas systems. When the failure was excavated, the location, we saw the slime, we saw that smell, and the later lab analysis showed that we were dealing with bacteria. Of course, when the corrosion product was analyzed, it was iron sulfide because we were dealing with sulfate reducing bacteria. So the questions we had was why we had water in the system, because we were supposed to be dealing with a dry gas system, and we found a lot of water in the system. And then the next question was where the bacteria were coming from. When we studied the system, we noticed that the sources of water were there were several sources of water. One, I've said, the gas refinery operating beyond nominal capacity. That means inadequate gas dehydration. Some refineries in the winter, when the demand for natural gas increases, have to increase their treatment capacity, and sometimes they exceed their nominal capacity. For instance, if a gas refinery is working as 500 cubic meter of gas per day, they increase it to 6 million 100 cubic meter of gas. About 20% of the gas, equaling 100 million cubic meter, will not be treated properly. That means it will not be dehydrated properly. So water is going through the system. The next source was that we noticed, unfortunately, for various reasons, probably the most critical ones, lack of quality control and supervision and communication with the hydrotest contractors. There were very poor hydrotest practices on site. No water treatment had been carried out. In cases, the water which was used for the hydrotest operations was not removed. Water was taken from any available source, and as I said, there were no chemical treatment, no oxygen scavengers were added to the water, no biociding had taken place. It was just, in many cases, groundwater or seawater used without any treatment. And then the next source of water ingress into the system was not removing groundwater in trenches during pipeline installation, repair, and maintenance. And some of this information came to us after I had left some of these companies as a trainer or as a consultant, because during my time, unfortunately, some of these information were deemed sensitive information, were not passed on to me. So it was afterwards that I was told that there were procedures in place. If trenches were excavated and there was groundwater in them, the groundwater had to be removed before any installation or before any repair and maintenance practices. But what was happening was that the contractor, with the excuse of not wasting any time, was making the excavations, and if they were filled with groundwater, no groundwater was removed, and installation or repair and maintenance were taking place in these trenches full of groundwater. I've got a few pictures that I will share with you later. Going back to the dehydration process, on this slide you see the hydration process in a typical gas refinery, where the lean glycol enters the tower here, the contactor tower here, and it contacts the wet gas which is entering the tower from the bottom, and then as this contact between the gas and the glycol increases, the dehydration progresses or take place, and then the rich glycol is taken to the glycol reboiler and the stripping column for heating, and through the heating the water is removed and lean glycol goes back to the tower. When you exceed the nominal capacity of your refinery, this particular system cannot do its job properly, and some of the lean glycol or the supposedly lean glycol which goes back to the tower is actually wet glycol. So dehydration or water removal is not taking place properly. And then the other problem we have got in the stripping column, some refineries, in order to improve this shortcoming, because they have already exceeded their nominal capacity, they increase the temperature by a few degrees in the stripping column, forgetting that when glycol is heated above a certain temperature, it will break down to glycolic acid or oxalic acids. And these are the acids which reduce the pH in the dehydration system, create internal corrosion, sometimes failures, and these failures would let oxygen into the system, which will promote higher corrosion rates. Here we have got a clip showing a gas distribution system which was not working properly. They had to introduce a break into the system. As you can see, water is coming out from this pipeline, from this point. The good news here is, as you can see, the water is clear. You can't see any visual sign of corrosion, judging by the color of the water. And this is a system which was supposed to be fully dry. Here is another picture of a trench taken by the operator when they paid a surprise visit to the contractor working site. As you can see, the trench is full of groundwater. It's dirty water. And I don't know whether it was taken during the installation process or the repair and maintenance. But again, the procedures for water removal had not been followed thoroughly. Here is another trench. Again, contractor was working here. The trench was not drained, and they kept working under these conditions. So new pieces of pipeline which were fitted, water would enter the system, and it was dirty water, and later we would get microbial corrosion. The next question we had, okay, we knew the sources of water ingress to the system, how bacteria were entering the system, how we would get bacterial contamination into a supposedly dry gas system. The first source was using out of spec hydrotest water to do the hydrotesting. And then the second source, as you saw through the pictures, was not draining trenches during pipeline installation, maintenance, and repair activities, which allow dirty water to enter the pipeline system and later manifest itself as microbial corrosion. There is this particular case here that a new pipeline system had been constructed to supply a city with a second source of gas. On the commissioning day, there was a big ceremony. Officials were lining up to take the photo. And upstream, they opened the valve, but downstream in the city where the officials were waiting, there was no gas. After a couple of hours, they broke into the system. And this is the clip we have received from that brand new pipeline, which was supposed to be carrying dry natural gas. Just look at the color of the water which is coming out of this break in the pipeline. See, opposite to the water which was coming out of the other pipeline, which was clear. This shows you can see a very brownish and dark water coming out of the pipeline, indicating heavy internal corrosion of the pipeline. And we realized later that the contractor had forgotten to remove the water after the hydrotest operation. So water was sitting there for months, and the pipeline had been corroded. This was a brand new pipeline to an extent that they couldn't use it to transfer natural gas to that city. So it was a waste of resources in every way that you look at it. Here is another case. Unfortunately, we had another failure when the system was opened up. A pit was excavated, and as you can see here, we have got a gas pipeline, and both gas and water are coming out of this break introduced into the system. Again, the good news here is, as you can judge by the color of the water, that no corrosion or very little corrosion had taken place, judging by the color of the water here. If I wanted to go through the root causes from what we discussed and what we saw through the pictures and the clips and the reports we had received, these internal MIC failures in the pipeline system for distributing natural gas. There were a few root causes. One was exceeding the nominal production capacity of the associated gas refineries. The other one was ignoring the relevant construction and maintenance procedures by not draining or removing the groundwater in the trenches during installation and maintenance. Inadequate quality control and supervision over contractors. Of course, if the first time contractors were doing their job like this, there was any quality control or supervision or checks or surprise visit, they would have not continued such a and professional practice when installing or maintaining and repairing pipelines. Lack of bacterial and MIC competency among relevant personnel. This is unfortunately a very common issue among many oil and gas operators. They are not very much familiar with the basics of MIC. They do not know what bacteria, what types of bacteria are usually responsible for microbial corrosion. They don't know anything about the severe corrosion rate associated with microbial corrosion, and hence they do not put into place any plans or any policies to combat or mitigate microbial corrosion, which often costs them a great deal. And the last one is inadequate communication between different parties within the operator itself and between the operator and the contractors. This is an example of inadequate MIC competency case of monitoring. When we talk about bacterial and MIC monitoring, the operator or its personnel should know that bacterial monitoring is separate from MIC monitoring. Each of these two subjects have got their own items. For bacterial monitoring, for instance, we can opt for liquid sampling, sessile samplings, using side streams, doing water analysis, using coupons, or analyze the peak trash. For MIC monitoring, we can do UT inspections, we can do pipeline intelligent pigging, we can use coupons or probes, we can also use peak trash analysis, or we can do failure or leak investigations. It's a very simple slide but shows you how different activities are associated with different types of monitoring for bacteria and MIC detection. And that brings me to the last section of this presentation, which are the proposed remedies. Obviously, we should not exceed the gas refinery's nominal capacity. We should always follow relevant company procedures during construction and maintenance activities for our pipelines. We should improve quality control procedures and contractor supervision. We have to provide proper and adequate MIC training for pertaining personnel. It's extremely important, not only for oil and gas, but for all other industries whose assets are susceptible to bacterial corrosion. And the last but not the least, improving communication between the relevant parties. And that brings me to the last note. Over the past more than 20 years that I've been working initially in the oil and gas and then in other industries, I've come to this very sad conclusion that unfortunately and fortunately, a significant portion of corrosion failures encountered in the oil and gas as well as other industries are due to very simple and trivial causes which could be prevented easily, promptly, and at no extra cost. I say unfortunately because when you are doing failure investigation, you see that you could have prevented the whole thing at the start if they had remembered to do very simple things. And I say fortunately because once you, as the representative of an operating company, know about the mistakes carried out by other operating companies, you will be in a very good position not to repeat the same mistakes. So here we are trying to share the lessons, and what I would like all of you to remember is that if you are currently dealing with a very costly, with very extensive, with a an apparently big corrosion failure, it doesn't mean that the root causes were also big and costly and complicated. It could have started from a very easy and trivial point and then developed into a failure. And that brings me to the end of this presentation. I would like to thank you all for your time and attention. Here you have got my email address and you have got my UK mobile and WhatsApp number. If there were any questions, feel more than welcome to contact me and send me your questions. I would like to thank Dr. Ali Morshed for his meticulous and professional approach to this presentation and the preparation for this presentation. It has been a great pleasure working for him, and thank you very much, Ali John, for your kind invitation, enabling me to share my experience with everybody through the Institute of Corrosion, the Midlands branch.
Thank you very much. Thank you, Ali. Indeed, an excellent and insightful presentation, and thank you for your kind words regarding me. And now we'll move on to the Q&A section. First of all, please write your question in the Q&A function. We may also have some time to take a few questions live. If so, please raise your hand and I can open your microphones. I can see multiple questions, so I start with the first one on the Q&A function. Ali, is there a proven relationship between the number of planktonic bacterial measured in a system and the sessile bacterial concentration?
I'm not aware of any such relationship. We don't know whether such a relationship exists. But what we have to remember is that unfortunately, most of the oil and gas operators, when they do sampling, they only sample the planktonic ones or only take fluid samples. We have to remember, apart from sampling, liquid sampling, we have to take biofilm or sessile or solid sampling as well. And that will tell us what is the number of planktonic bacteria in the system, what is the number of sessile bacteria in the system.
All right, thank you very much. So the next question is, the value of water show water in liquid or gas phase? So there's a question based on one of the slides that you showed. Is it the value based on the shale gas spec or any standard followed?
Oh, you are referring to the dry gas definition that I offered. Is the value of water show?
Is it the shale gas spec or is the actual?
This is the shale gas spec or the gas which leaves the refinery. I've seen in different countries when the gas leaves the refinery, they have got a definition for the gas downstream of the refinery. And these numbers I provided are coming from various operators which use the same numbers.
Thank you. Next question, will MIC cause problem in deaerator column and glycol regeneration system? How it is managed if there is a potential for it? So you mentioned that there's a kind of, they increase the temperature, or there might be some problems with regard to.
Usually when you get MIC, if it's severe MIC, if the population of bacteria increases, then you will get slimes in the system, and these slimes, wherever you have got heat transfer, they can degrade the heat transfer, whether when you are injecting chemicals into the system, these slimes and biofilms can detrimentally affect your chemical problem, the chemical injection. So MIC will cause problems in the aerator column and the glycol regeneration. I've seen the aerator columns opened up and they were full of green stuff or slimy stuff because there was no proper chlorination upstream of the aerator column.
Mhm. And so how is it managed? So it should be managed based on
when you have got a deaerator column in place, because it offers a very high surface area, because you want to improve the efficiency of oxygen removal, you have to make sure that upstream of the tower you are injecting chlorine into the system on a continuous basis. There are some operators who have moved the biocide injection point even upstream of the deaerator or DA tower. But they have to remember that the main function of the tower is to remove oxygen. Some of the biocides which are injected upstream of the tower, they increase foaming, and foaming detrimentally affects the efficiency of the aeration. So these are the things which we have to take into consideration.
Thank you very much. So let's take one question from the audience. So Aladdin, I think, has got a question. Aladdin, I think if you turn on your mic, you can ask your question. You're on mute, yeah. We cannot hear you, so. Okay, let's try again. I have another attendee, Ahmed. Ahmed, I allow you to talk, so go on. I think you are also on mute, so if you can turn on your mic. Ahmed, please go on.
Is there any temperature limit for MIC? Beyond that, we can say there is no potential for MIC?
We have got various type of bacteria which can function and stay active in different temperatures. I don't know off the top of my head what are the limits, but of course there is a sort of linear relationship. As you decrease the temperature, you see bacterial activity decreases. For instance, for the same type of bacteria in the British North Sea and in the Persian Gulf region, we see more or less for the same type of bacteria in the Persian Gulf region, because of higher temperatures, the bacteria are more active, they create more corrosion. In the North Sea region, in the British section, the same type of bacteria, because the temperatures are far lower, are less active, and they are relatively less dangerous, sort of considering the role of temperature here.
Thank you.
You're welcome.
Thank you. So back to another question from Q&A function. Ali, what tests do you recommend for detecting and monitoring sessile and planktonic concentration within a system?
This is a good question. You know, we are in a sort of transition time. Traditionally, we used to use the culture-based methods where you would take samples, liquid or solid samples, and put them on a culture. And after 30 days, you would look at the culture and try to count the number of bacteria. For the past maybe 17, 18 years, we have been moving toward microbiological, molecular microbiological methods, or DNA-based methods. In my humble opinion, the best approach is that we use both systems together. We take samples and we put them through the culture-based method and through the molecular methods. And among the molecular methods, I believe qPCR is one of the most common ones, and they are easier to use, and they can give you the results in a very short time.
Thank you.
You're welcome.
So we have, let's get back to Aladdin. I'll ask you to unmute once again for last, and let's see if we can speak. Aladdin, can you? Yeah. Do you want to ask a question? Please speak. Unfortunately, we cannot hear you. Maybe a kind of mic problem. So I get back to Q&A function. Sorry, Aladdin. We have, so one question is from Kennedy New Conta. So he's asking, is the predicted MIC corrosion rate of up to 5 millimeter per year also applicable to CRA materials, or is it for carbon
The
steel?
5 millimeter corrosion rate I quoted, it was something I had seen myself in a system made of carbon steel, so that rate is associated with carbon steel. Of course, if we move from carbon steels to CRA material, that rate would drop as we increase the amount of nickel and chromium in our alloys. They become more resistant toward MIC. So that rate is simply associated with carbon steel. And one point I have to remind everybody, for those of you who are trying to raise your questions through the microphone, if for any reason you couldn't raise your question, share it with us. Remember, in the last slide, I had my email address. Feel free to send me an email, and I will try to answer your question to the best of my ability and knowledge.
Thank you.
You're welcome.
Okay, next question. So it's from Mohammed Metwali. He's asking, what is the maximum safe limit for SRB, and what is the standard talk about the limit?
I don't think there is any standard limit for SRB. Different operators, based on their operational experience, have come up with certain limits, and they say, for instance, up to this point in our system, the maximum allowable amount of SRB is, for instance, 100 SRB per milliliter, or 100 SRB per square centimeter. Regarding international standards, I don't believe there is a safe limit defined anywhere.
Okay, thank you. Next question, Muhammad Taha Anis asked, what laboratory test do you recommend to confirm that internal corrosion in a dry gas pipeline was actually caused by MIC? You alluded to that point.
Yes, it was a culture-based method. The traditional culture-based method was used, and then the corrosion product itself was analyzed, and iron sulfide was discovered at the failure site, which is an indication of the presence of sulfate-reducing or SRB bacteria.
Okay, thank you.
There
are many questions. Sorry, I go by one. Thank you very much for answering very concisely in order to cover all the questions. So with glycol carryover from operation above nominal capacity, how does the biocidal effect of MEG influence MIC activity in the pipeline? Is the biocidal effect reduced due to saturation of MEG?
That's a good question. Unfortunately, I don't know the answer to this.
Okay, thank you. Next question is from Nerdosh Mobeth. Can you get accelerated MIC for more than 5 millimeter per year in sulfuric process systems?
I don't know about sulfuric process systems. As I said, the 5 millimeter per year rate, I had encountered it myself, but I have heard from my other colleagues that the rate they had encountered was up to 8 millimeter per year in upstream assets dealing with MIC problems.
Okay. We have one question which is not relevant to the topic of this call. So it is with regards to how to become senior corrosion technologist. So we will respond to this question via email through the
Yes,
database that we
if
have.
they send me or email me, I will do my best to guide them.
Okay, thank you. Next one is from Susan Ozbek. Does MIC usually happen at 6 o'clock position in the vessel as well as pipelines?
Most of the time, yes. When we get MIC or bacterial corrosion, it's at the 6 o'clock positions. In tanks, in some tanks which we use for storing fuel, sometimes is the fuel contains some water instead of the bottom or the 6 o'clock position. We witness MIC at the interface of the fuel and water. So it could be 10 centimeter, 20 centimeter, or half a meter above the bottom line, depending how much water there is in that tank.
Thank you. So we have another hand raised from Ian Nugraha. I allow you to talk. If you open your mic, you can ask your question.
Hello, can you hear me?
Yes,
Yes, yes, loud and clear.
Okay. I want to ask, what field evidence is strong enough to justify calling a corrosion case MIC instead of only possible MIC? Thank you.
Sorry, can you repeat your question?
What field evidence is strong enough to justify calling a corrosion case MIC instead of only possible MIC?
You are asking what evidence do we need to have as a minimum to call it MIC? There are a number of parameters which have to be fulfilled. First, we have to find out whether we have got bacterial contamination in the system. The lab test or the lab analysis will tell us that. Second is that from a metallurgical point of view, we have to find a product which is the result of bacterial corrosion. If we have got, for instance, SRB in the system, we should expect to find iron sulfide in the system. So this was number two. Number three is that we have to have favorable conditions for the bacteria in order to be able to survive and remain active in the system. If all these three conditions are met, then we can say with a good degree of confidence that we are dealing with MIC in our system.
Okay.
Thank you, Dr. Ali.
Oh, you're welcome.
Okay, so if you mute yourself, thank you. So next question, Ali, how accurate and reliable is method of taking sessile bacteria sample from corrosion coupon surface during routine retrieval for corrosion monitoring? Do you think it is?
Well, it depends on the procedure we use to take the sessile samples. Of course, there are procedures written. If you look at those two NACE documents that I had included in the table in one of the slides, I believe one of them at least explains how sessile samples or solid or biofilm samples have to be taken, how they have to be preserved. And the emphasis here is that if we are going to do any analysis on them, the analysis should preferably be taken place on site. Because if we want to send the sample somewhere kilometers, sometimes thousands of kilometers away, there might be some changes happening to the sample. And unfortunately, we have had cases where samples were taken, solid samples or liquid samples, they were not preserved very well. And what we got from the lab was that there were no bacteria in the system because during the transition, all the bacteria were killed. For instance, if you're dealing with anaerobic bacteria, that means the bacteria which will be killed or become inactive in the presence of air, you have to put your samples immediately in an airtight container. Otherwise, the oxygen in the air will kill your anaerobic bacteria. So these are the points which have to be taken into account.
Thank you. Next question is from Richard Owusu. So he's asking, he wants to ask you how what is culture-based method to identify SRB. He wants to know more about this culture-based.
Okay, if he can send me an email because it needs a bit more explanation, I can send him some sources with which explains. I believe what is important is the sampling itself, the conditions under which we take the samples. Because if the sampling is not done properly, then the lab, even if it's the most or the best equipped lab in the world, will be doing analysis on a piece of sample which is contaminated or which has been tampered in different ways. So sampling here is extremely important. We have to take into account the location of the sampling, the timing with regard to the last chemical treatment, the orientation of the sampling, whether the sample is taken from the 6 o'clock position or the 12 o'clock position. If he can send me an email, I will do my best to send him a more comprehensive answer.
Thank you. We have a very good question. Next one is, an anonymous attendee asking, is there any direct relationship for increase of corrosion rates through coupons may indicate presence of bacteria, either sessile or planktonic? So the next part of the question is, industry using ER probes for corrosion rate monitoring. Although deposit of iron sulfide layer may lead to false readings. What's your thoughts on that? So
this is a very good question. Personally, if I'm dealing with microbial corrosion in a system, I would prefer coupons over probes because coupons give me more information regarding the type of corrosion which is happening compared to probes. Of course, probes can provide you with a live feed of the corrosion rate in the system, but coupons, when you remove them, you can see whether you have got pitting or not. You can see whether you have got erosion or not. If you have got scratches on your coupon, if you have got bacterial corrosion, there is a chance for you to remove the slime on the coupon, send it to the lab for further experimentation. Coupons are easier to retrieve to service. Personally, I would go for the coupon option rather than the probe option.
okay. So you prefer coupons over?
Yes, it's my personal humble opinion.
Yeah, okay. And it's very valid. Thank you.
Yeah.
So we have getting more questions. So it's okay. One attendee asking, will the slides of the presentation be shared for your information? If Doctor, do you have any problems of sharing the slides with me?
No, what I will do, there are a few clips or photos which have copyrights. I will remove them and email the rest to you so you can share it with our audience. And what I would like to reiterate here, MIC is a very insidious corrosion deterioration mechanism. It can hurt us very badly. But the good news is that the basics of bacteria and MIC are very easy. If we educate ourselves on the basics of bacteria and MIC, we can prevent or we can mitigate a lot of MIC cases in our assets.
Perfect. To just complement what you mentioned, so when I receive the slides, I can upload it on ICorr Midlands page. So if you go to ICorr website, there's a subsection for Midlands, and we regularly upload any slides that or any presentations that we have during the webinar. So you can download it from there. There is another good question. What is considered a nutrient for bacteria? Is there any species within the transported fluid that bacteria favor as the nutrient, which promote bacterial growth?
Okay, see, bacteria need carbon as their main source of cell reproduction. They need hydrogen. Depending on the different bacteria, they might need nitrogen, sulfur, and maybe a few other elements. If we know what type of bacteria we are dealing with, we would know what type of nutrition might be needed. For instance, seawater naturally has got some sulfate in it. I have forgotten the average concentration of sulfate in each cubic meter of seawater. But when you have got seawater coming in and you have got sulfate reducing bacteria, seawater naturally has got this sulfate as a nutrition, and the bacteria can use it to create corrosion. If we know what type of bacteria we have got in the system in terms of its metabolism, then we would know what are the carbon sources or what are the other nutritional sources for the bacteria to be used in the system. And hopefully we can stop or reduce the ingress or the presence of such nutrition in the system. One thing we have to remember, some of the chemicals we add into the system in order to mitigate corrosion or combat corrosion, they could be considered as nutrition for bacteria themselves. Unfortunately, there has been a few cases where an oil and gas operator was injecting biocide into the system, and the biocide acted as the nutrition for bacteria. And each time they injected biocide, there was a hike in the corrosion rate. And later we found out what they were injecting was not killing the bacteria, but helping the bacteria to grow and become more active.
As a food to them, yeah.
Exactly.
Last question from the audience. So, and I have one question for the end of this session. So this question is, does MIC take place at high flow rate liquid piping? When we have high flow, does it contribute?
No, MIC for bacteria, in order to be able to convert from floating to stock bacteria or to convert from planktonic to sessile, they need very low flow rates or stagnation. Remember, bacteria most of the time enter the system in a floating situation, i.e. as planktonic. If the flow is reduced or the flow becomes stagnant, then they have the time, they have the opportunity to gradually precipitate toward the bottom of the system. And it's usually near the walls or near the interior surface of the system where we have got higher concentration of nutrition, which helps them to become more active. So higher flow rates do not promote MIC.
Okay, thank you. And my last question that I want to ask from my side. So my favorite topic is risk-based inspection. As you know, we do not have a very good kind of logical corrosion rate calculation for MIC into RBI codes and recommended practices. I want to know if you have any such experience of combining using your knowledge in MIC to incorporate with the RBI system for a plant.
Yes, that's a very good one, Ali John. When you are reviewing your RBI methodology, of course, you are assigning risk values to different areas or location of your system. Those risk values are coming from the probability of the failure and the likelihood, the probability of the failure and consequence of the failure. Probability itself is a function of various things like the presence of solids in the system, the flow rate, and the type of the material used. If you want to include MIC in your failure risk assessment methodology, then the result would be a risk-based inspection, I would say, framework, which is more accurate in terms of pointing you to the areas where MIC could be taking place. So you have, if you want to have a better targeted risk-based inspection plan, considering MIC, you have to go to your failure risk assessment methodology and see if any of the inputs relate to bacteria or not.
Okay, thank you. That's the last question. I would like to extend my sincere thanks again to Dr. Ali Morshed for sharing his expertise, experience, and valuable insight with us this afternoon. On behalf of the ICorr Midland branch, I would like also to thank all of you for joining us and for your active participation in today's discussion. I hope you found today's webinar both informative and relevant to your corrosion and integrity management activities. Just a reminder again, our next webinar is scheduled for 23rd of July at 4 p.m. UK time, and will cover the validation of CMI, current magnetometry, inspection for pipeline corrosion assessment, which is delivered by Mark Glinka from AMPP. Also, please keep an eye out for upcoming ICorr Midland technical events and webinars through our social media channels like YouTube and LinkedIn. Become a member and subscribe. And thank you once again. Enjoy the rest of your day, and goodbye. Thank you, Dr. Morshed. Bye.
Ali John, thank you very much. Bye-bye. Bye-bye, everybody.